All right, so this is Module 7, and what we're going to look at is in a little more depth the idea of functions. So we've seen a few already in previous modules, but now we're going to include the math library, which gives us a wide range of different functionality. And we're going to pay attention to and think a little bit more about how do we actually call functions and how they're actually working. So if we're following along in the textbook, this is actually loosely covered. It's not exactly the same set of functions that we're going to talk about here, but it's covered in section 4.2. So we did a little skipping. We're going to double back to chapter 3 in some of the next modules. All right, so what we've seen already is in previous programs that we've written, we've used two different functions. One of them was the size of function. And the size of function, I think we use as an example, it allowed us to figure out how many bytes on a particular machine, a particular data type, or in fact a variable as well, was used, or how many bytes was used to store those given pieces of data. We've also seen the time function, and the time function was a little strange in that it returned the number of seconds since January 1st, 1970. But we kind of had the idea that it would return a different number, obviously, for each period of time that we called it. Size of would return a different number of bytes for each data type. So let's think about the word function, and I think it's useful to map it back to something that you might have learned in algebra in a regular math class in terms of functions and linear functions. So when we first learn about functions in algebra, we think of it as y equals f of x, right? So f would be the name of this function, or it symbolizes some sort of a function. X is the parameter or an argument into the function, and then y is the value that is produced. Y is the output or the return value of the function. So from a math perspective, we might have something like y equals f of x. Let me increase my size here, where f is equal to x squared, right? So if f is equal to x squared, so y is equal to x squared, then of course when x is equal to 2, the output y is equal to 4. When x is equal to 3, the output y is equal to 9. The idea being is that the output for every single output in a mathematical function, you're going to get an answer. You're going to get a y value. Perhaps it's going to be unique, although that's not guaranteed. So we can have functions. So if we think y equals 2x, for instance, a linear function. If this is the x-axis, this is the y-axis, 2x might go something like this. Y equals x squared, of course, would be a little bit different and would follow a different path. Now, when we think about functions in C++, we're not really thinking about drawing graphs or anything like that. We're really concerned about, or we're really kind of taking the abstraction for a particular x value, we're going to output a particular y value, right? So in C++, the idea of a function is not reserved just for like a mathematical function, something that you would graph on a piece of paper or something like that. It's the concept that we've got some sort of operation that's going to be done on the parameters, on the arguments. In a mathematical function like y equals f of x, the value of the x-axis, the position that you currently are on, is the argument, and the output is where you land on that function, where the output of that function is. So in C++, the arguments don't need to follow a regular number line. It doesn't even need to be one parameter. It can be a lot of different possible values. We'll have functions that accept strings. We'll have function that accepts characters as parameters. The return values can be of any data type, so it's not necessarily limited to a number line like a y-axis. But the concept's the same. You send input into the function, all right, so x, and you get an output. Now, in addition, we're not actually limited to having one set of one parameter into our function. So in math, if you cover calculus, and you actually start thinking about the functions that can define surfaces, you'll deal with functions that accept 2 parameters and 3 parameters and 4 parameters. It's a little bit more complex in mathematics as you go into those type of functions. But in C++ or in programming speak, a function can accept any number of parameters. So we can have a function that accepts A, B, and C, and those might not even be numbers. Those might be 3 different strings. Those might be 2 numbers and a string. But we're going to take that output somehow in that function. That function is going to take that input, and transform it. And it's going to compute based on code, and we'll later learn how to actually write our own functions, but it's going to use some C++ code to take those parameters and transform them into some value y. So when we go back and we look at size of and time, size of accepted a parameter in double, float, boolean, and it had some code inside. It has some code inside of it to transform that input, int, double, into the correct number of bytes and return the number of bytes. So we can say int bytes equals size of int, for instance. The time function is a little bit odd because actually we only call it with 0 within the context that we've used it. So the input is always 0, but it's outputting some new value each time. And that's a little bit of a strange, it's a little bit of an exception to the rule where the same input actually transforms to different outputs each time because it's at a different time. Now, examples that kind of really illustrate or kind of more easily kind of map to our concept of functions in mathematics is, of course, functions that are defined in the math library itself. So C++ comes with a math library. It's called cmath. The C stands for the C programming language. And it's got functions in it that will allow us to compute a variety of very commonly used mathematical transformations. So for instance, we can use the square root function. We can pass it a double, right? Pass it 9, pass it 18, pass it whatever we want, and it will return back to us another double that's the square root of whatever we asked it for. The sine function can accept any value, and it's actually assumed to be in radians, not degrees. But you can pass in any value, and it'll return the value of the sine function, the cosine function, the tangent. So all of our trigonometry functions, and there's arc cosines and there's arc tangents. The absolute value is a nice little function that can take any number and it'll always return the absolute value. So if we pass in -5, it'll return back to us 5. And there's actually many, many others. We don't really need to exhaustively go through the entire math library quite yet. Notice that the power function takes 2 different parameters. The power function takes a base and an exponent, and it will return the base raised to the exponent power. So we'll go through a couple of examples of using this. In order to use cmath, or the cmath library, just like we use ctime to use the time function, we have to include that. We're going to do a pound include cmath. That's in addition to IOStream. Perhaps that's in addition to ctime, although that's not required. We only need ctime if we're using the time function. Note that on Visual Studio, if you're using, I know at least 2012 and 2013, the cmath library is automatically included. It's actually included through the IOStream library. Try not to get used to that. Don't rely on that. You should always explicitly define all the libraries that you use in your C++ code. Other compilers will not automatically include cmath, and your code won't compile. So you want to keep on top of that. So let's just switch over and write a couple of little examples just to test this out. I'm gonna experiment a bit with the power function. I'm gonna have, let's just say value equals power of, and let's do 2 or 3 raised to the third power. And again, although this will compile on Visual Studio, I want to definitely include cmath explicitly. And I should certainly print that value out. And we'll build it. Okay, and so we can see the answer is 3 to the third is 27. It's returning the correct number, and this can work for any values, right? So we can plug in anything, 13 to the 2.5 power, which is a much more difficult thing to sort of get your head around and calculate in your head. But you can see that the power function can return it. So the answer of 13 raised to 2.5 power happens to be 609. So this will work with any value, and of course we can use this function as many times as we want, so we can keep reassigning it. Let me just copy this value, or copy that bit of code, and let's do 2 raised to the third power. And we can keep calling power function with different values or different parameters each time, so maybe 9 squared. And so when we run it, we see each and every answer. It's the power function. Inside these parentheses, we've got the function name, we've got the parentheses, and we've got 2 parameters separated by commas. And that's the syntax for calling functions. The parameters themselves, the base and the exponent. So this is returning back to us 13 raised to the 2.5 power. This time I call power, and it's going to return 2 raised to the third power, 8. This time I'm calling power with 9 raised to the second power. And functions themselves can be called with parameters that are expressions. So 9 minus 2, or 9 minus 7, sorry, which will equal 2, could be raised to the value power. Right? So this is going to return 81. Value will be 81. If we go 2 to the 81st power, I don't know what that's going to actually be. Probably quite big, actually. So maybe let's make this a little bit smaller. 3 to the second power. We'll make it 2 to the 9th. So this is going to return back to us 3 squared, 9. And then the power function is going to be called with 9 minus 7. That's an expression. That'll be evaluated to just be 2. And then this will be 9. The value is being passed in as that parameter. So 2 to the 9th power is a little bit more easy to handle. 2 to the 9th is 512. So functions can be called with different parameters within your code. Parameters can be variables. They could be expressions. They could be very long expressions. In fact, they could be calling other functions. So this is sort of a strange little example, but here I'm calling power with 2 parameters. The base happens to be the result of a power function call. So 2 to the third, of course, will be 8. And then we're going to raise 8 to the 9th power. And that's what we'll get. And you can notice that very large numbers tend to print out in scientific notation. Now we're not limited just to the power function, right? So we can call square root. Maybe you get the square root of 9. That will, of course, return 3. So we should see our 609 value. We should see our 8, and then 3 now instead. And then, of course, this is going to be 8 raised to the third power. And 8 raised to the third power ends up being 512 as well. So the point here is that we've got a number of different functions that are going to be available to us through this cmath library. Calling them basically works the same way each time. Now, why did I use two two numbers here and one number here? Well, you have to know the context. You have to understand what those functions really do. Square root, it doesn't make sense for a square root to take more than one parameter. You're trying to find a square root of a single number. If you want to find a square root of two numbers, you got to call square root twice. You would have to say, something like value, let's do double value 2 equals square root, I don't know, 4. All right? And of course, it doesn't have to be an even number. We can calculate the square root of 5 as well. Power has to accept two parameters because we need to know the base and the exponent. There are many functions that accept dozens of parameters. Right? So there's no limit on the number of parameters that we actually use, but it's going to depend on which function we want to call. It will be illegal to call square root with multiple parameters because square root does not accept that. Square root's not defined to do that. And we'll learn later on in a few modules how to define our own functions and how these functions are defined. Likewise, there are also functions that do not accept any parameters. We'll see one coming up soon called the random function. And that's perfectly acceptable if that function is defined like that. Of course, square root requires you to input one parameter. Okay, so let's take a look at an example. Here's a kind of a real-world physics type question where we can now build a program knowing that we understand how to compute the square root. We can write a program to do this. So the formula to figure out how much time an object takes to fall from a particular height, and we'll allow the height to be entered in by the user. In our formula, I'm calling it x here. The time it takes an object to fall depends on its height, and it depends on the acceleration of the object. Now, any object on Earth accelerates at a rate of 9.8 meters per second squared. We'll include that as a constant in our program for now, but of course we could ask the user for the acceleration, and they could calculate how much time it would take an object to fall if it was on the moon or on some other planet. So we're going to let the user enter a distance for this case. We're going to write a constant for our acceleration, and we're of course going to use the cmath library to provide our square root formula. So I want to start by just reinforcing the whole input, calculation, output type procedure first. Hopefully we're getting good enough about thinking about problem solving that some of these simpler programs start to become second nature. But we're always going to start with our flow chart, right? So we've got inputs, our calculation, and then our output, which would probably include the input from the user as well. We've got some variables here. We've got distance, and that's an input. And it'll probably be a double. It's a height. We've got acceleration, which is not really an input. It's not coming from the user. It's just a const. 9.8, certainly a double. And then we've got time, which is an output or a calculation. And it should also be a double, right? Because it's certainly not going to be an integer necessarily. And we've got that dependency where distance needs to be known before time. Right? Our time is equal to the square root, and I think what was it? 2x divided by a. And whether we call it x or we call it distance, it doesn't really make much difference. And there we go. Now, one thing that we want to remember as we're going forward with this program is the square root is actually being taken around this entire term. So it might do us well to actually calculate this term as a temporary variable and then compute the square root of that temporary variable. We need to be very careful about that. We don't want to do the square root of 2 times distance and then divide the whole thing by a. So at this point, once we've mapped things out, it's a fairly simple process. We can start writing our code. I'm going to get rid of the code we started with here. And I'm going to write my variables, distance, and I'll say distance and time right on the same line. They're both going to be doubles. I will have a const double. I'll call it A equals 9.8. And of course, that's meters per second squared. Right? And the reason I write that in the comments, it's probably not all that important, but we need to remember as we're writing the program and we're writing our prompts to ask the user for those specific types of units. So the input into this problem, the only input that the user is responsible for giving us is this distance right here. That's the only input we've got. So I'm going to say, please enter height to fall from, and I'll explicitly prompt in meters. Certainly if the user's typing in feet, if they're typing in yards, they're typing in centimeters, our calculation technically will be right, but of course the user won't get back exactly what they think. So we'll try to make sure that we echo back out the input so the user is reminded that we were interpreting their numbers as meters. So we'll read in distance. And we've already got our cmath library, remember, included up here. So we can go ahead and use the square root anytime we want. I am going to create a temporary variable. Let's just call it temp. And I'm going to make that equal to this 2x divided by a. So x was distance divided by acceleration. In terms of precedence rules or anything like that, of course, multiplication and division happen at the same level of precedence. This is going to be a left to right calculation. Since double is a distance, the 2 times distance is a double divided by another double, so we don't have to worry about integer division or anything like that. Once I have that, I can say my output is equal to time, or my output time is equal to square root of temp. Now, if I want to go ahead and instead write this, time equals square root of 2 times distance divided by a, that's perfectly acceptable as well. So whether you like to use these temporary variables or not is up to you. As equations get larger, most people start to include more and more temporary variables. Once we have that, let's do our output. Let's first output the distance. And again, I'll reiterate the units of measure. And I'll output what the acceleration value is. And there's really no way to write that exponent out, so we'll leave it like that. In fact, let's put the units right afterwards. And now we'll print out the time. And of course, that's in seconds. So our entire program is fairly straightforward. We've got our inputs, we've got our outputs. Really, the new part here is the fact that the calculation just isn't a regular operator. We're actually using one of our math functions. So let's say I'm falling from 100 meters. It'll take me 4.5 seconds to hit the ground. Now again, it's hard to necessarily trust this data, right? So what we want to do without question is to run some calculations. Maybe you want to open up a spreadsheet and you want to type in your formula, if you want to do it with a calculator. But by some method, you should be checking your numbers. You should be making sure that these numbers make sense and that they're correct. An easy way to do it is sort of input some basic numbers, 1 for instance. If we think meter of 1 meter, we plug that in, 2 divided by 9.4, take the square root, and we can punch that into a calculator and check those numbers. Right? So I can't stress enough that, offline, outside of our recordings here, we would certainly want to go through and check all these numbers. Now, although the function, the program itself is fairly straightforward, there's a few more outputs than normal maybe. We've used some functions, but importantly also this is reinforcing the use of units, echoing out to the user what we're interpreting these numbers as. Right? We always want to keep that in mind. And this slide just kind of summarizes that idea. It's very, very frustrating for a user to run a program and not really understand what they're being asked for. And I want you to get into the habit of always thinking about things from the user's perspective. You doing some extra work on the programming side is always well worth it, because your program's probably going to be run, hopefully it'll be run by a lot of people, it'll be run for a long time. And so those extra few minutes that you spend making the experience of using your program easy is worth it. It is absolutely worth that time and effort. This will always yield a much better user experience. So in summary for this module, it's fairly short, but what we see is that we're starting to open up a whole world of different functions that are available to us in C++. So while later on we'll learn, how could we actually implement our own power function, our own square root function, we know now that we don't necessarily have to always do that. There are lots of libraries within C++ and provided by other people that we can include. So we included cmath, and then we can call. We can call those functions to calculate fairly complex numbers, right? So calculating the sine and cosine of different values is not necessarily that easy. That's a complicated process. Once you understand how to call a function, any function, you understand how to call all functions. It's always the same type of method. What you do need to know is, of course, how is the function actually defined? Right? So does the sine function accept degrees or radians? This is something that you don't have to look in documentation. If you Google the sine function in the cmath library, you'll have lots of documentation on this. So let's just prove that out. And of course, you can use your textbook for this, but you want to start to get used to using Google, using search engines to help you out with C++ and any programming. I'm not ever gonna. I would not actually recommend trying to program without any resources. There's typically way too many functions. There's way too many modules in a programming language to spend your time memorizing everything. What you need to do is certainly get really used to being able to find the information when you need it. So let's imagine that I wasn't quite sure how sine worked in cmath. I can just Google sine cmath, and your first hit on Google usually is the cplusreference.com. That's good. Certainly there are others. And we can start looking at it. So we can see the documentation on this function itself. We see returns the sine of an angle x in radians, and it's got an example on how to use it. So we should never really be completely without or never be stuck because we don't actually know what a function or how a function works or how a function should be used. All of these C++ functions are certainly documented, and we can always find those pretty easily. That's not to say this is the only reference. There are many, many references. So from this point forward, you should be able to remember that the cmath library is probably going to help you deal with a lot of the different mathematical operations that you might encounter It won't deal with them all, right? So there'll be some functions, there'll be some operations that you're going to have to program yourself. But having a good resource and starting to look at that cmath library will save you quite a bit of time.